everybody survive? I think I got everybody back. Jeez. All right. So let me ask you this. So I've told you already, we're going to have 3 of these things. So I'll tell you right now, I'm going to say this again. We're going to have 3 formulas to construct confidence intervals. They are all going to have plus or minus in them, which only makes sense because then it can go down and up, and that's how you make an interval, correct? What always trips me up is the only time you use those formulas is if I say construct or find the whatever percent confidence interval. That's the immediate clue that you use one of the formulas with a plus or minus in it. There's no reason to use it anywhere else. Okay. But just looking at this, remind me, what was this part called again? Error. So let me write that down by itself. Holy shit, that's a weird looking cigarette. Okay. So let me see if this makes sense. The problem we just did, we took a sample of 37 dolphins, correct? And we ended up, on part A, we ended up with an error of 1.324. Okay. You guys should know this. If I wanted to make the error smaller, what do I need to do? And I don't want to change the confidence, right? I want to still be 95% confident, but I want to make the error smaller.
Increase N.
Yes, get a larger sample. That makes sense just from a conceptual, bigger sample, good, right? But mathematically it makes sense because the bigger n is, the smaller this gets because I'm dividing by n, essentially. So it should make sense then that if I have an error that I want, let's say instead of 1.324 inches error, let's say I want to have half an inch. I want to be off by half an inch. Now my question becomes, well, how big does n have to be? I know 37 sample size gives me this error. Now the question is, what sample size will make the error 0.5? If it's like 100, then we're like, okay, I can do that. I can go take 63 more dolphins, that'll make 100. Are you guys with me? If the answer is 1,000,000, I'm like, okay, I can live without being that close. So this is what I call a feasibility study. You guys heard the word feasible before? Is it doable? Right? Is it reasonable for somebody? So if we had to go take a sample of 100, we could do that. If I said go get a sample of 10,000, it's cool for you to go, no, no, Jeff, no, because that's crazy. Okay, which means I want to actually solve this for n. If I have a formula where n equals something to do with the error, I can just throw the error in and figure out how big of a sample I need. This works if I know what the sample size is, I can figure out there. So I just want to turn this around. How the hell do I solve this for n? Well, what really sucks about n in this equation? Where is it? It's on the freaking bottom. So anytime I have an equation with fractions in it, do you guys remember from algebra what you do? If you have fractions in an equation, what's something you can do? Multiply by the denominator. If you do by the reciprocal, you're gonna make other fractions, right? So if I multiply both sides by the square root of n, I'll end up with, let me do it like this. All right, that cancels. So trying to get n by itself. So what do I want to do next?
Divide by E.
Yes, I want to divide the e the hell out of there. Get the e out. This is one of those algebra intense moments that we're going to have a few of. Very few. Now somebody else tell me I want n, not the square root of n, so what do I do? Square both sides. So I end up with n equals z sigma over e squared. So if I want to be off by 0.5 inches or within 0.5 inches, where would 0.5 go in this equation? And for E, that's how much I want to be off by. All right, so look at part C on the handout. What was that? Okay. So you see on part C? So again, just remind you guys, a sample size of 37 leads to an error of 1.324. I already know that. Now I want my error to be 0.5. So you could have it like this. I actually prefer this. I don't know why past Jeff put it down like that. They're both the same thing. I have to square everything, but 95% confidence. What was the z-score again for 95%? Yeah, so 1.96. Standard deviation we know from the beginning was 4.11. And now I want the, if I put a 37 here and do the work, I'm sorry, if I put a 1.324 here, n is going to be 37. We already know that. I want the error to be 0.5 now. So what this formula does is if I know what I want my error to be, I can actually calculate how large of a sample I'm going to need to take. And then I can see if it's even feasible to do that. So let's see what we get here. Don't forget the square. Let's see, 8, 16, I'm going to say 197. Is that right, Jeff? I don't know. We'll find out. That doesn't seem right. Hold on. 250, no.
I got 259.
Thank you, okay. What'd you get exactly?
259.57.
What would this mean? What does n mean again? Be more precise about this problem. What does n mean in this problem? No. Number of dolphins. This scares me, right? Because I'm easily scared. No matter what the hell that is, you round it up. Even if it was 259.0003, because I need at least this many to have an error within 0.5, so of course I'm going to round up. If I take, another dolphin, then I'm definitely going to be within 0.5. Does that make? You always round that n up if it's a decimal. You guys kind of with me? Does that seem feasible? We've already taken a sample of 37. Well, now it depends. We're not actually on the boat. I don't know how long it took to get the sample of 37, right? So it'd be up to them. Does 260 seem like something we could do? Yeah, exactly. That's sort of like a number that's not. If it was 50, that's only 13 more dolphins. I would think that they could. But if it was 1,000, we're like 260. I don't even know if there's 260 dolphins there, right? And how long would that take? And all right, you guys roughly with me? Okay, I like it. So the formula as it's given here, this piece, if I know the sample size, I can figure out how off I am with my sample mean, roughly. This just does the reverse. If I know how off I want to be, I could figure out how large of a sample to get. So what kind of problem do you use this formula for when it says something like how many? Because how many is n. How big of a sample? N. How large of a sample? N, right? How many people? N, right? Okay. So I use the formula that solved for n. It kind of makes sense. No worries. So what do we get here? 260. Okay. Even if it was 259.0003, you still round up. Okay. Now, last thing for today. Don't get too excited. It's going to take a little while. Actually, I tell you what. Before we do that, let's do one more quick example of this kind of confidence interval. So let's say we take a sample of 38 dogs and find, somehow we do this, a mean anxiety level of, I don't know, I'm just gonna make this up, of 27. And like, 10 is a normal level, let's say. And this is, all right, I don't know how you feel. When I was a little kid, I lived in Florida, and fireworks were just, you could do. And my God, I'm so happy I escaped that time with all of my limbs. Because holy shit, we were done. Hold the bottle rocket, hold it, no, throw it. It's like, oh my God. Anyway, sorry. So now, living in California, just right for a freaking fire. And then you got, I don't know how you feel about it, but if you're okay with fireworks in neighborhoods, just keep it yourself. And we'll stop. Okay, so one thing is that, of course, dogs and veterans are affected by loud noises and such. All right, stop. Let's take a sample of 30 dogs. We find a mean anxiety level of this after the fireworks, right? It is known that the population standard deviation is 5.82. Create the 94% confidence interval for the true mean level of anxiety in dogs after the fireworks. Blah, blah, blah. So, I would never teach like this, but now that we've gone through the derivation, I've thrown the concept at you, you've picked up from it what you could. I know I'm making a confidence interval for a mean, right? And I know, what symbol would this be? Sigma. So we know sigma, and I want a confidence interval for the mean. Because one kind of confidence interval we're going to make is for a percentage, and then it's going to be like P plus or minus. It's going to have percentages in it. So obviously I don't want to use that one. I don't want to use the confidence interval formula that has an S in it, because we know sigma, correct? So then I know I'm going to use this formula here from the 3 that we're going to have eventually. And now you just step back and you go, what do I know? Do we know X bar? Yeah. So X bar is, wait, what was X bar? No, X bar is what? Try it.
27.
27. What's 38?
That's bad.
N.
Wrong. What?
And what's sigma? 5.82. 11. So what's the only, yes, sorry.
I'm just double checking. So we're using sigma and not S because even though we have a sample of 38 dogs, we know that the mean
Where
anxiety
did
is
this
for-
come from? Did this come from the sample?
No, that's what I'm, yeah,
Yeah.
because that and the mean anxiety both came from the population, and now we're looking at the sample, right?
This, where'd that come from?
That came from the population.
No.
That didn't come from,
No.
no.
We take a sample of 38 dogs and we find the
Oh.
meaning. So that came from the,
That came from the sample.
yes. If that was mu, we're done. I wouldn't do anything.
Oh, that's
Yeah.
what we're looking for.
Yeah, we're trying to get a feel for what
okay.
mu really is.
Okay. Right. That makes sense.
So again, the whole idea behind this is any sample mean I take is almost definitely wrong. Wrong in terms of it's not the actual population. This is just sort of a low-level kind of attempt to get a feel for what the real mean looks to be.
So I can see where I kind of went wrong. I don't know if other people are thinking the same way, but normally, or what I'm used to us doing in class, or sometimes it's like, oh, if we're doing sample stuff, we use these sets of equation if we're doing population with these steps.
Sure.
But for this, we're using both X bar and sigma, which have come from two different things.
Totally.
But we're doing that because we're using this stuff to look for stuff.
Exactly. Yes.
Okay.
Now, section 8.2 is where we're going to develop a formula. It's going to look almost exactly the same, but it's going to have an S here. It's going to have something different here because you will see why. But it's going to look basically the same. So it's kind of weird that we know the population standard deviation, but it's not impossible. There are situations where we do. So we're trying to get we don't know what the shit that is, but we do know what this is. Now the reason this is true, this is for all dogs. This is for our sample of certain dogs. Doesn't that sample of certain dogs live within all dogs? Therefore, the standard deviation of all dogs is still true for those dogs themselves, because they're still a part of that, aren't they? So that's why this type of problem could still exist. I still like 8.2 better, because normally we don't have a freaking clue, right? We found some new species of spider. Now I'm thinking about arachnophobia for some reason. We found a new species and we don't know shit about it. So what's the average length? What's the standard deviation? We don't have a freaking clue. So we don't know what sigma is or freaking mu is. So if I want to make a confidence interval for their average length of the spider, then I need some other formula. I can't use this one because that's if I know sigma. Okay. So we know X bar, we know N, we know sigma. So the only thing we don't yet have is what? Z-score. What part of what I've gotten up here is going to tell us what the Z-score is?
94%.
Yeah, 94% confidence. So is that part of the baby chart? Anybody understand what I mean when I say baby chart? It's a little tiny chart on the side. Okay. It's not in there. Damn it. So you got to do it the old-fashioned way. You got to earn it. So 94%. So let me say this real quick. This is going to make a lot more sense when we get to this section, but when I make a confidence interval, can you guys tell me how many tails I make? Look at the picture. What looks to be a tail? How many tails are there? 2. Okay, good. So a confidence interval, chop, makes 2 tails, and it's symmetric. Boogie, woogie, woogie. So that's why there's 94% inside. There's how much outside? So there must be 3. It doesn't matter which z-score I find because they're both the same number, just one's a negative, one's a plus, which is why there's a plus and minus in the formula. So I'm going to find the negative one because that's easier. What percentage is in there? 3%. If you look on the z-score chart, careful, 0.03 is not a z-score. So you got to look at the body. What's as close as you can get to 0.03. I think do I have any left for myself? Stats teacher without a z-score chart? Here we go. 0.03. What do you guys?
You're getting 1.88.
Oh, there it is. Yeah, cool. So the closest I could get is 0.0301, which is pretty damn close. And that's 1.88. Is everybody with me? The worst this kind of problem could get is if they don't give me X bar and S, but they give me a list of data. Well, then I just put them into list 1. I do 1 var stats. I get X bar and S. Are you guys kind of with me? Most of the time, they're just going to tell me everything except Z, and then I got to look that up. And now we got it. So now we can actually construct the formula. So what's the formula going to look like now? X bar. 27, give or take. 1.88 of the standard deviation, which is 5.82 divided by the square root of 30. Let's see. You gonna try to do it in your head? Yeah. 1 point.
25.22504.
No, tell me what the error is. I think it's 1.7 something.
Minus.
What is the error? Really? 1.77, I like it. Every now and again, I get lucky. All right. Let me stop for a minute. All right. Calculating the error first just makes mathematical sense, because now I can just put 27 minus that, 27 plus that, instead of having to put the whole damn thing in twice. Also, the homework and I will ask you for the error by itself. So calculate the error. So now if I do 27, give or take 1.77, what do we get?
to 28.77.
I like it. I like it a lot. And of course, is that done?
No.
No. Right? Time for everybody's favorite part. Right? The conclusion. We are 94% confident. It's pretty good. That what? The interval. They make a big deal out of something I haven't made a big deal out of yet. 25.23. Well, this is a bad example, damn it. There's no units. So this is one where you can get away with this. If there are units, you must include them, or else I'm going to be a complete dork. So if this was like number of hot dogs somebody could eat, and you put 25.23, I'm going to say tons of hot dogs. You know, I'm going to be, and you're like, all right. So there is no. I didn't put any units on this imaginary level. So the interval 25.23 to 28.77 contains the true. You can kind of plagiarize the true mean level of anxiety in these dogs. Wow. So my English counterparts, I'm sorry. There will be a couple times this semester where I just say, just plagiarize. But that's a very specific, right? This is what we're trying to get a feel for, so of course that's going to show up at our answer, right? That only makes sense. Not in general. Don't ask ChatGPT to help you. You guys know ChatGPT?
Heard of it, never used it.
Oh, all right, real quick. It's stupid awesome. I showed a colleague of mine, I typed into ChatGPT, create a test, it was a different thing, but create a test about creating confidence intervals. Blah, 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 just make, now say, and then make an answer key for the test you just created. Blah, 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 blah. Now that's dumb. Yeah. If I'm you, I'm not going to type that shit in. You go in there. Here's what I did. Create a short horror story in the style of Mark Twain about porcupines, and it will just do it. It will do it. And then you say, do it again, and it will do it again in a different thing. Yes.
Have you seen the workarounds with ChatGPT about because it censors itself for dangerous stuff? If you're like, hey, how do I make napalm? It'll say, I'm not going to tell you that, but if you say, hey, pretend you're my grandma who worked in a napalm factory.
Yes.
It'll be like, oh, I need you to
There's so much. There's so much. But I will say this. I tested a few things out. I asked it to solve a few problems, and it does make mistakes sometimes. It's not a math engine. It's just a general knowledge kind of, it really is just a sophisticated search engine. Because all of its answers come from the internet. It doesn't know shit. Yeah.
So I guess from what I've heard, kind of the way it works, is it basically just puts one word after the other and ranks the words by likelihood as to when they would come after them.
Yes.
And then it adds a little bit of randomness to it, and then that's all it does.
Because and if you ask it to write a paper about a specific subject, it'll look that subject up. It'll construct the paper. If you ask it to write it in a certain tone, it will then look at examples of things that have that tone, and then it will generate based on the tone, right? It's really fun to play with. I'm really sorry. This is not an ad break. sorry. I don't have shit to do with ChatGPT. It's just out there. It's just interesting. It's just something to play with. It'll actually construct code for you if you're a programmer, and then you can say debug this and whatever. Anyway, I'll stop. Why did that come up? Oh yeah, because I just made a joke about ChatGPT. All right. So how do you guys feel about this? I mean, this kind of problem is so beautiful because, again, it's just plug and chug. Right? And you all have heard that expression before, right? I remember one semester a student thought I was saying something offensive, and I'm like, no, plug the stuff in, chug the answer out. Right? So I was like, I don't know what you're thinking I'm saying, but okay. Now the last thing for today. So several things that go into this. Real quick, what have I been careful about so far with the sample sizes?
Above 30.
Above 30, right? If I give you a confidence interval problem where the sample is less than 30, what else must I say?
It's normal.
I have to tell you it's normal, right? So either I tell you it's normal and the sample size doesn't matter, or the sample size is more than 30. If neither of those are true, you can't do shit. That would be a stats 2 problem, and unfortunately, we don't offer stats 2 here yet. I'm working on it. I'm not sure how many people I get to take it, but now, so for means, n greater than 30 or normal given, right? It's given that it's normal or n is greater than 30. Otherwise, I can't do anything. What's the one step in the problem? They're gonna give me x bar, they're gonna give me sigma, they're gonna give me n. What's the one step where if I don't know that it's normal, I can't do? What's the one step? Yeah, I can't use this. This only works for normal curves, so that's a huge step because then I can't figure out the z. Okay. What we haven't talked about yet, and I'm so happy right now because I normally completely forget to do this until I've given you something to work on. I'm like, oh shit, I forgot something. I'm not going to find this quickly, but remember the, yeah, that's fine. Remember the handout that had the basically the pyramid looking thing, right? It was the, holy crap, it was the, we flip a coin so many times, right? You guys remember that? Yes, okay. You're all like, let's just say I do. Keep going. Okay. And the highest bar was at 7, right? And we said it looked roughly normal, correct? So we're getting into the point now. We're gonna do section 8.3, and one reason I do 8.3 before I do 8.2 is 8.3 still uses z-scores. 8.2 uses something different. You're gonna get a different chart. Ooh, yay. So that's why I kind of like to do 8.3 and 8.1 before I do 8.2, because we're still using z-scores for 8.3. So we're about to get into P. That sounds weird. Into percentages. Okay. So for means, I know exactly what test to look for if it doesn't tell me it's normal. We don't have a test yet for percentages. We have to figure it out. So can somebody tell me, what was the lowest, this was all about the number of heads I flipped. What's the lowest number of heads that I could flip? 0. And this was if I did it? Sure, Jeff. If I did it 14 times. What's the highest number of heads I could get? 14. Holy crap. Okay, so there's these 2 walls, correct? And the whole distribution has to live within them. Let's say I have a coin that's weighted, meaning the probability that it comes up heads, let's say that's 0.1. You guys semi with me? Actually, let's make it even worse. Let's make it 0.01. Yeah. So 1 out of 100 times this coin will come up on the head, right? So that's a good coin to have in case you're like, all right, we'll call it tails. Oh, look at that, I did it. Right. If I flip it 14 times, what's the expected number of heads? Yeah, to get the expected number, which is the mean, I do n times p. What's 14 times 0.01? 0.14. Yep. So I would expect, on average, so if I flip this coin, well, 14 times I get 0.14. If I flip it 100 times, I expect to get 1 head. Are you guys with me? So now what's the picture going to look like? Where's the tallest bar going to be? It was at 7 when it was 50-50. Isn't the tallest bar going to be right here at 0? And then it's going to go like this. Correct? Does that look like it has any chance to be normal? No. That's skewed right. Yes. Okay. Left, right. You guys semi with me now? What the shit are you talking about, John? Please, dear God, just say something in English. Here's the idea. Let me see. I got enough up here we can talk about the idea. If the mean is far enough away from this wall, it has a chance to go up and come down. So that, and the mean is NP. So NP, here's what we determined. NP has to be at least 5. If it's at least 5, it's got room to come up and then go down. So if NP, let me put it up here, sorry. If NP is at least 5, that's good. But isn't there another wall? If P is 0.01, what's Q? 0.99, right? So not only do I have to check NP, I have to check NQ. I've got to make sure that I don't run into the other wall. I don't have the opposite problem. So NQ also has to be at least 5. So for means, it's n greater than 30 to be normal. For percentages, NP and NQ have to be at least 5. That's what you check. And it's really kind of cool. It's a visual. Pull it far enough from that wall, but don't push it so far it gets too close to the other wall, and then it has room to be normal. So now we've solidified, if I have a binomial situation, how do I tell if it's going to end up with a normal curve if I plotted all the probabilities? NP and NQ have to be at least 5. Then it would be approximately normal when I graph it. Okay, that's one thing right there. That's huge. So we all, at this point, n greater than 30 is sort of ingrained in us. Yes? N greater than 30, it's just, we just know that. That's got to be the same way now for percentages. Okay, I love it. Next thing, that some semester I'm going to remember to make a big deal out of this, but I didn't this semester too bad, Jeff. Every time we've been given like a PQ problem, NPQ problem, the P has been a population percentage. The very first problem we did, 11% of Americans are left-handed. That's 11% of all Americans. That's a population, correct? Blah, blah, blah. So just like we have a symbol for a population mean, and we have a symbol for a sample mean, we also have a symbol for a population percentage, and we have, get ready. See how the X has got a little hat on it? Okay, so the P gets a little happy. It's got a little hat on it. It's got a little party hat. This is a sample percentage. This is called X bar. This is called P hat. I appreciate it. Huh?
It's actually called P hat.
It's called P hat. That's not my name for it. I know some of you guys are like, that's what you call it. No, that's the name of it. It's the thing you don't want to wear. Don't wear the P hat. Doesn't sound like a good time. Okay. Okay, so those are some ground level things before we even construct the formula for percentages. Remind me, what's the formula for the mean of an NPQ problem?
And C.
No, not probability, just the mean.
Oh.
NP. And the standard deviation?
Square root of NPQ.
11. So what is the formula for an NP if I've got sample percentages? What's the sample mean if I have sample percentages? N times P hat. And the standard deviation would be the square root of N P hat Q hat. So now, if they're wearing hats, it just means they came from a sample. No matter what clothing they're wearing, P and Q have to add to be 1. P hat plus Q hat is 1, P sock plus Q sock is 1, P whatever. There is no P sock, by the way. It's not statistics. Okay. Alright, so now we're ready. Let's construct this formula. So let me come back. Do you guys remember when we constructed this formula, we actually started with this. That one we knew from chapter 2. So let's do the exact same thing. But now, in place of mu, I have to use x bar, which is n times p hat. So now I'm going to put the stuff that relates to my problem. So just like we put x bar for sample mean instead of mu, because we don't know what mu is, we're now going to use np hat. Give or take z. And what am I going to put here? Square root of np hat q hat. Okay. By the way, right now, this is the derivation of a formula that you'll never have to do yourself. We're deriving a formula. The formula we're going to use, but I want to show you where it comes from. Somebody with me so far? We have just directly substituted it for percentages. What's that? This. What's that? This. Right? That's all we've done. What is this formula for? I love that kind of question. What is that formula for?
Error interval.
No, the whole thing. Yeah, to make a confidence interval. What's the purpose of a confidence interval? I'm trying to catch what? The real mean. So I'm trying to catch the real mean in there. Yes? So what am I trying to catch here? Aren't I trying to catch the real mean?
Trying to catch the mean.
But what's the real mean for NPQ problems? So I'm trying to catch what NP is. Okay. Stop for a minute. This is all really weird, I know. Okay. Now, in the news, don't we just see 40% gonna vote for this person, 42% gonna vote? Aren't they just percentages? Give or take 4%? Yes? Is this just a percentage yet? What do I want to get rid of so it's just a percentage? I want to get rid of n, yes? So let me divide both sides by n. Then what am I catching? I'm catching the real percentage. Now believe it or not, there's something we can do mathematically to this. Can I just cancel the ends? Why can't I just cancel the ends? How many ends are up top? I love this question. How many ends are on the bottom? 1. How many ends are up top?
Square root.
Half. There's half of an n up top. Why can't, so for example, what's the square root of 10 divided by 2? Is that the square root of 5? Nope. What's the square root of 10 divided by the square root of 2? That's the square root of 5. I can divide if they're the same root. again, we're kind of delving just a tiny bit into algebra. What's the square root of n squared?
And
So can't I replace this with the square root of n squared?
oh, now
That's the, I love that answer. Sure. Do it, man. Do it, math boy. No, I'm sorry. That's just funny to me. Now can I reduce the n's? How many n's cancel?
half.
1. Right? Doesn't 1 n cancel? So here is what the formula is for the confidence interval for percentages. And you're all like, ooh, what a reveal. So it's still our data, give or take this many. What is this going to represent then? We're going to use this later. What is it in the place of? What does that represent this here? Standard deviation. This represents the error. This piece must be sort of like a standard deviation. And we're going to actually use it later. Because isn't this formula our mean, give or take, this many standard deviations? Our percentage, give or take, this many standard deviations. There you go. Okay. So we're going to steal that later, use it somewhere else. Okay, so now we've got our second official confidence interval formula. Let's try a quick problem out. What time we got? We got time.
11:17.
Thank you so much. Let's try out a quick problem here. We talked to 158. I don't know. Real estate agents. And 17 say they love their job. Well, that's pretty bad job. What do I have against? I don't know. I want to find the 99% confidence interval for the true percentage of real estate agents that love their job. One thing I want to point out, it definitely should feel like I'm not giving you as much information. I haven't really told you anything. Half of this thing is what I want you to do, right? So just this piece is information. What the shit, Jeff? Well, what did we actually know? Can somebody tell me anything we know from what I've told us?
We know n is 158.
Beautiful. N is the bigger number. Right? I mean, 17 is a part of that, yeah. So we talked to 158 people. N is 158. Can somebody figure out what P hat is? What does P hat represent again? P means a percentage, and the hat means it comes from a sample. So what is the sample percentage?
It is 17 over 1.
Yeah, it's always got to be less than 1, right? Don't say that this is 17. Whoa. 17 out of 158. So somebody help me out. 108? Yeah. Look at you go. P hat, Q hat have to be at least 3 decimal places. So again, going along with what I said earlier, if you just make everything 4 decimal places, except for z-scores, you're pretty much covered. All right, so it's up to you. Can somebody tell me what Q hat is then?
0.991. Oh, 0.891.
Yeah.
I bet.
All good. Say again? 892, yeah, thank you. Even better.
I can't do math, I'm sorry.
Neither can I, it's all good. Now, before we start throwing stuff into the formula, what is the one thing we don't have for the formula yet? Z-score. And of course, that's gonna come from this, but before I do that, what do I have to check to make sure I can actually legally look at the chart? Is it normal? And what do I check to see if it's normal?
Sample size are given. Or
Sample size not good enough.
sample size greater than 30.
Nope, not good enough.
Just gonna be P.
I'm not talking about means here. N P hat, N Q hat. Let me see if, yeah, greater than equal to 5, I love it. Exactly. Let me see who gets this. What's N again? 158. When I multiply P hat times N, don't I get 17? Or if you don't trust me, what is 0.108 times 158? You will get really close to 17. Right? P hat times N. What do you get? Exactly?
0.06.
Well, yeah, you get basically 0.17. You get 17. So P hat will always have N on the bottom. So N P hat will always be the number they gave us. That's a shortcut. Do you have to remember that? No, you just take P hat and you multiply by N, and you're going to happen to get close to this. All good. So is that good so far?
Yes.
Yes, because it's greater than or equal to 5. Check. What's N times Q hat? Well, I would just do 158 minus 17, the rest. I would get 141, but somebody help me out. What is 0.892 times 158? I haven't implanted my calculator in my hand yet.
141.
Dude. Huh?
141.
141, holy shit. And that's at least 5. Check. What does that mean? The thing we just did?
It's normal.
It's normal enough. So we're allowed to look at our z-score chart now. This is exactly the same as n greater than 30, but n greater than 30 is not good enough for percentages. That's what I use instead of n greater than 30 for percentages. So what is the z-score that you should be able to look at your little baby chart for this?
0.575.
Yeah, 2.575, I love it. So now we got everything we need. Before I get too far, there's all these little bits and pieces I always forget until I can talk about this right now. So if I ask you to draw a 99% confidence interval, like we did earlier, all that means is to draw what on there?
Normal curve with
Chunk, right? Chunk. Can somebody tell me how much is in this tail?
0.05%.
0.0?
Or sorry,
Oh.
0.05.
0.05. Nice. So you're right, 0.5%, 0.005. Now here's what's really kind of cool. And how much is in this tail?
Same thing.
So what's the total in the tails?
What? No.
1%, 0.01.
Yeah.
You guys all with me? There's a symbol that is the Greek letter A, which makes sense because it talks about the area A in the tail or tails of the situation. So the Greek letter A, lowercase, is alpha. And in this case, what's the area in the tails? 0.01. So you are going to see this. Actually, pretty soon you're going to see it a lot. All it means is the area in the tail or tails. So see how I say, what's a confidence that will always make? How many tails? Chop. 2 tails, yes? Confidence interval always makes 2 tails. Pretty soon we're going to look at situations where it's a 1-tail situation. Right now, I don't know if anybody can imagine what that would mean, but it's coming. Okay. Do I have everything I need to throw into the formula now? Yes. Put it up here. So P hat, 0.108, give or take 2.575 times the square root. I don't need this. I don't need you. P hat, 0.108 times Q hat, 0.892 divided by 158. Now this is gonna suck in terms of making sure you put this in your calculator correctly. For those of you who have a newer calculator where the square root just grows, that's awesome, because then you can make sure all of that shit's underneath. If you have a calculator and when you hit the square root button it looks like this on the screen, do not close a parenthesis until you're done putting all the shit in there, right? If you close a parenthesis, you come outside of the square root, you're not gonna get the right answer. So everybody try to figure out what the error is, don't say anything yet. Scheiße. All right, who thinks they have the error?
I got like 0636.
Yeah, 0636. Yeah. You guys all get that? Whoever's playing along? Yes? Okay. And now you just do the same thing as before, and then the conclusion is gonna be basically the same. So what's 0.108 minus that? 0.0444? Is
Yep.
that true?
Yes, sir.
Neato. I wish you could say I did it on purpose. And then 0.1716. Is that right?
Yep.
Sweet. Look at me go. Now, remember what I said earlier, when you go to write your conclusion, you must include units. For this kind of problem, the units will be percentage. You change that into percentages. So, the conclusion sounds exactly the same. It's still a confidence interval, that's all it is. We are 99% confident at the interval 4.44% to 17.16% contains the true percentage of, see now you can plagiarize. Real estate agents that love their job. Okay. Good luck reading that. So sorry. If you wanted to be able to read your teacher's writing, you have chosen poorly. Now, your gut reaction to that, 4% to 17%. What do you think? Is this evidence that less than a quarter of real estate agents love their job? Is this evidence that less than a quarter love their job?
Yes.
Totally, because this is entirely below 25%. Is it evidence that more than 5% love their job?
I would.
Nope, because 5% is inside the interval. It could be less than 5%.
Even if most of the interval is above.
Even if.
Okay.
Totally. I like it. In terms of showing evidence for something, confidence intervals are a little bit wobbly. They're not solid evidence, but they're sort of like a ground level evidence. The next chapter we're going to get into after this one is going to be what we actually use to test claims. And that's going to be where we start to talk about, is it enough evidence, is it not enough evidence, that kind of thing. You can still ask evidence questions, and I will, but confidence intervals aren't really built for that. Okay, that's plenty. I think we did a lot. That's plenty. So on the other side of the handout, we'll do that other side next time. That talks about the percentage stuff. So we'll do that next time. yeah, so come up and see me if you have any questions. Otherwise, you can run away and have a good weekend. I hope.